All right, let's talk about machine learning. It's one of those terms that gets thrown around everywhere, and it can sound kind of like magic, but it's not. It's actually a really clear step-by-step process. And to prove it, we're going to walk through your very first project together right here, right now. So let's dive in. So this is the big question, isn't it? How does a machine actually learn? I mean, we say it all the time, but what's really happening? Well, it's way less sci-fi than you might think. Just imagine a student who's incredibly patient, never gets tired, and just keeps getting better and better with practice. That's kind of what we're talking about. You know, this classic definition from way back in 1997 really nails it. Let's make it super simple with something we all use, a spam filter. So, T is the task, flagging spam. E is the experience, that's you, hitting the spam button on junk emails. And P is the performance, how well it catches spam in the future. The more experience you give it, the better its performance gets. Simple as that. Okay, to make this all feel a bit more real, we're going to go on a little quest. We're going to build a system with a really clear mission to predict housing prices in California. And this is a perfect first project, trust me. It's concrete, and it's going to let us touch on all the key steps you take in any machine learning project. So here's the game plan. We're going to feed our program a bunch of data about a neighborhood. You know, stuff like the median income or how old the houses are. And in return, we want it to spit out a prediction for the median house value. In the world of machine learning, this is what's called a regression task. We're not trying to classify something as A or B. We're trying to predict an actual number. And this is where it all starts. Not with some abstract idea, but with a big, real table of data. Each row you see here is a district in California. Each column is a feature, its location, how old the homes are, total number of rooms, you name it. This table right here, this is the experience that our machine is going to learn from. But hold on, before we can just throw this at a machine and say learn, we have to do our own homework first. We have to understand the story that this data is trying to tell us. And I'm not exaggerating when I say this is probably the most important step in the entire process, data exploration. Seriously, you have to put on your detective hat here. Raw data is never perfect. It's messy, it's got missing pieces, weird outliers, and all sorts of hidden patterns. Our job is to find all those clues. If you skip this step, it's like trying to build a house on a shaky foundation. The whole thing is just gonna fall apart later. Check this out. We've just plotted two things here. Median income on the bottom and house value on the side. And as you'd probably guess, there's a pretty clear upward trend. More income, more expensive houses. Makes sense. But do you see that? That perfectly straight horizontal line near the top? That's a data quirk. It looks like somebody just capped all the most expensive houses at $500,000. If we're not careful, our model could actually learn that cap as a rule of the universe. This is exactly the kind of secret a data detective is looking for. Okay, so now that we've played detective and we understand our data a little better, it's time to pick our tool. We need to choose an algorithm, which is really just a fancy word for the method our machine is going to use to actually learn from all those numbers. Now, at a super high level, you've basically got two main ways to go. On the left, there's instance-based learning. Think of this like a student who just memorizes every single flashcard. When you ask a new question, they just flip through their brain to find the most similar card they've seen before. Then you've got model-based learning on the right. This is more like a student who actually learns the underlying formula or concept. They build a general model, which lets them solve problems they've never even seen. For our housing project, we're definitely going with this model-based approach. But which model do we pick? This brings us to a really fundamental idea in machine learning called the no free lunch theorem. And all it really means is that there's no single magic algorithm that's the best for every single problem. You just can't have it all. For housing data, a simple line might be best, but for finding cats in photos, you need a super complex neural network. The only way to really know for sure is to try a few and see what works. You got to experiment. All right, it's time to meet the big villain of our machine learning story. It's called the overfitting trap. And this is all about the danger of a model that learns the training data too well. The source material for this whole thing gives a perfect analogy. Just imagine you visit a new country for the first time, and the very first taxi driver you meet totally rips you off. If you walk away from that thinking, okay, all taxi drivers in this country are thieves, well, you've just overgeneralized from one single bad experience. Machines can make that exact same mistake. And that's exactly what overfitting is. The model gets a perfect A+ on its homework, the data it's already seen, but then it completely bombs the final exam when it sees brand new problems. It hasn't learned the general rules. It's just memorized the specific answers, including all the random noise and weird quirks. It memorized the noise, not the signal. Just look at the difference here. On the left, you've got a nice, smooth curve that captures the general trend. That's a good fit. Now look at the thing on the right. That model is way too complicated. It's twisting and turning just to hit every single little data point. It's not learning, it's memorizing. And that model is going to fail big time as soon as you show it something new. So we've explored our data, we've picked a model, and we've learned how to avoid the overfitting trap. Now, the really cool part is realizing that these exact same steps, this whole process we just went through, this is the engine behind so many incredible technologies we use every day. So let's just take a quick tour of what this process really unlocks. Because whether you're trying to understand pictures or teach a robot how to walk, the power comes from applying these very same core ideas. For instance, machine learning can find hidden patterns in super complex data. In this example, an algorithm was just fed thousands and thousands of pictures of clothing. With no help, no labels, it just figured out how to group them by type. It put all the t-shirts in one pile, all the boots in another. This is called clustering, and it's basically how a recommendation engine knows what you might want to buy next. It can also be used to really understand what's inside an image. This is called image segmentation. The algorithm goes through and groups pixels together to identify that, hey, this part's a flower and that part is the grass behind it. This is absolutely critical for things like self-driving cars, which have to know the difference between a person and a street sign. Machine learning can also take something that looks incredibly complicated and make it simple. So take a look at this Swiss roll. It looks like a messy 3D jumble, right? But the real pattern is just a simple 2D sheet that's been rolled up. These algorithms can digitally unroll that data to find the simple, useful structure that was hidden inside all the noise. And finally, there's reinforcement learning. This is so cool. Imagine an AI learning to play a video game. It's an agent that learns by pure trial and error. It just mashes buttons, gets points when it does something good, and gets penalized when it messes up. And after millions of tries, it develops a strategy, a policy, that lets it win. This is how AI has mastered everything from chess to really complex video games. So, after all that, what are the big takeaways from our little quest? First, machine learning is a process. It's not magic. Second, it always starts with a clear question and usually some pretty messy data. Third, you got to remember there are trade-offs when choosing a model. There's no free lunch. And finally, and this is the most important one, the real goal is not just to perform well on old data. The true goal is to generalize to new situations. Which, brings us to one last really big question. The tools for machine learning are more powerful and accessible than ever before. So the challenge for us isn't just about how machines learn anymore. It's about deciding what are the most important, the most beneficial, and the most interesting things we should teach them next.